Okay. So first we'll just go over some theoretical principles. So finite element analysis, or the finite element method, it's a numerical modeling method for solving problems of engineering and mathematical physics. And it's especially useful for problems with complex geometry, loading, and material properties where analytical solutions cannot be obtained. In other words, finite element analysis is used for higher-end analysis, or projects that require more detailed or thorough calculations. So first, let's take a look at the analytical solution, which I'm sure you're all very familiar with. It's typically used for simple structures, and it's based on dramatic simplifications and idealizations. Therefore, it's ideally used for, once again, for simple projects, and it's very limited when it comes to complex or more finer analysis types. And the design is based on calculation results of idealized structures and large safety factors. So overall, with the analytical solution, although it's very easy and very simple, it does tend to give overly conservative calculations, especially for higher end projects. And then for finite element analysis, the design geometry is much more complex, and the accuracy requirement is much higher. So we need to understand the physical behaviors of complex objects. For example, things such as, whoops, sorry, my PowerPoint's acting up on me here. So yeah, as I was saying, we need to understand sort of more complex parameters such as strength, heat transfer capability, fluid flow, which is especially useful for seepage, etc. And we use it to predict the performance and behavior of the design, to calculate the safety margin, and to identify weaknesses of the design accurately. So ultimately, with the finite element analysis, although it requires more effort to conduct, you do get more accurate results. You can get more optimized designs that will ultimately cut costs. And through the use of finite element software, which is becoming more prevalent in the engineering industry nowadays, all engineers will be able to, I guess, use finite element analysis with greater confidence and with greater ease, to the point where finite element analysis will be, start to become more used in the analytical analysis. So the first and main thing that you need to understand about finite element analysis is the idea or the concept of discretization. So discretization is essentially just a process that we go through of dividing or separating a body or an element into smaller pieces to simplify or to get more accurate results. So for example, if you have a piece of material here, what we'll do with finite element analysis is we'll cut it up, or we'll separate it into 3 different finite elements. Or with larger elements, obviously, you'll have large sets of finite elements. These elements will be connected at certain points here called nodes. And then just through a series of theoretical, or excuse me, a series of differential equations that are all linked, we'll be able to calculate the nodes, the displacements, as well as the stresses and strains. So finite element analysis is closely tied to matrix calculations, but we won't get too in-depth about that. These are just the main concepts that you need to understand, is that with finite element analysis, you're able to take large elements and sort of divide them into smaller elements to get more precise results than you would be able to with an analytical solution. So now let's take a look at the different types of finite elements that we have available to us. So first we have 1D elements for trusses and beams. Then we have 2D or plate elements, which are used for example, 2D. At the end of this session, we'll go over some 2D examples, and we'll rely highly on 2D or plate elements. And then we have 3D or solid elements, which are used obviously for 3D calculations or higher end type projects that would require analysis in 3 dimensions. So keep in mind that every time you add in a dimension to your analysis, the longer it takes. So say, for example, if you have a bridge that you analyze with 1D or line elements, and you can do that with finite element analysis, you can use idealizations of beams, and the analysis will be relatively fast. But for example, if you were to use plate elements for that bridge, say you modeled all the flanges with plate elements as well as the girders, it would take you longer to model and the analysis would be longer, but your results would be much more detailed and complex, or more detailed and more accurate. And then the same applies for 3D analysis. Once you start using solid elements, the analysis can take quite a bit of time to run. But once again, for today's seminar, we'll focus mainly on 2D elements. And then later on, as we get more in-depth in later sessions, we'll go into 3D analysis as well. Okay, so here's just a couple of examples of finite element analysis. Once again, you have a truss modeled with 1D elements or beams. And then as you go more detailed, for example, if you use planar elements or 2D elements, these are typically used for example, retaining walls, slope stability, seepage, embankment type applications, which we'll go more into detail later. And then we have solid elements, which can be used for 3D analysis of, for example, slopes, or of other certain applications that we'll go into more detail later. But just once again, keep in mind that with 3D elements or with solid elements, you'll be able to achieve the highest sort of level of analysis. But once again, the effort and the analysis time will take much longer. So there are certain trade-offs with each. Okay. So now we'll move on to our next section, primary steps of finite element modeling. So finite element modeling consists of 6 major steps. Or first and foremost, we'll designate the sign convention and unit system, very straightforward. Next, we'll select the types of finite element analysis. So depending on the type of analysis you want to run, you'll have several from which to choose. Then you need to select the dimension of your finite element analysis. Once again, 1D, 2D, or 3D elements. Element types, you'll need to generate the FE mesh or your discretization, which I'll go into more later. And then last, we'll define the boundaries. We'll sort of go over how you can assign different boundary conditions based on your project scope. Okay. So first, let's go over sign convention. So in midas GTS, this is just the sign convention for stresses and strain. Compression is negative and tension is positive. So just keep that in mind. And then also, pore pressure is defined as negative for hydrostatic compression. Okay. Then the analysis type. So all of these analysis types are available to you in midas GTS. So as I'm sure you're already aware, it's a very flexible program. So static, construction stage, seepage, which we'll go over today, stress seepage, semi-coupled analysis, which we'll go over later on, and then, okay. Oh, I'm sorry, I think I have a couple of comments here on, some people can't hear me very well, so let me once again just adjust the microphone. So sorry about this, this hold up, guys. Okay, so I think that should be a little better. And also, I'll try to speak more slowly. I know I'm sort of rushing through it. I just want to make up for lost time, and so hopefully we can get to the modeling sooner. Okay. So let's just review over the different sort of analysis types. And once again, as you begin to gain more experience with the software, these will become more familiar to you, and you'll be able to sort of recognize them right away. So linear static, which is, we use elasticity and we get isotropic as well as anesotropic results. Nonlinear elastic, here they're just the different sort of constitutive models that are available to you. So for those of you who've taken geotechnical engineering in college or have taken your master's, these should all be very familiar. You'll all be very familiar with them. So we don't need to dwell on them. It's just, this slide is just to help you understand, what's available to you with midas GTS. And then construction stage analysis, which is especially useful, for example, excavation type problems or projects, where you can have one model file, and over the course of that model file, you have several stages with different sort of stages that better simulate how your excavation or how your project is done over time. So, for example, if you can model temporary structures, you can do staged or short excavation. And then seepage analysis, once again, which we'll go over today, so you can study steady state as well as transient regimes to see how the pore water pressure changes as the water level changes. You can account for different rainfall conditions, etc. And then seepage stress and semi-coupled analysis. So this is particularly useful for example, maybe slope stability problems or projects where you'd want to analyze the effects of seepage or rainwater on the stability of your slope. And once again, you can assign your pore pressure results as mechanical loads. You can assign different stages as well as construction stages to see how your slope is affected over each stage, over each section of, say, construction or rainfall. And slope stability analysis. So most of you, I'm sure, are aware with the limit equilibrium method, which is the most typically used method for slope stability analysis. But later on in upcoming sessions, we'll go over how to use finite element analysis for slope stability to get maybe results that are more accurate or more optimal than that are possible with the limit equilibrium method to determine better factors of safety. Okay. And then third step is to select the dimension. So once again, for plane strain or two-dimension, you can use that for static analysis as well as axisymmetric. Seepage analysis is usually done in 2 dimensions, and then three-dimensional or solid type finite elements can be used for all analysis types. So let's go into a little bit more detail here. So with plane strain, once again, it's a 2D analysis, and what you'll do is you'll take a certain slice of a structure, and you can analyze the effects of stresses and strains and loads on that structure for that given section, and you can extrude it along the z direction. So in other words, if this structure here is uniform in the z direction, just being able to calculate the effects of loads or moments or displacements on this one section will allow you to calculate, or will allow the program to calculate the effects on the entire length of the structure or the element. Same with axisymmetric. So once again, as you can see, this structure here is symmetric down the middle. So once again, if you can analyze successfully this one section, the program, or midas GTS, will be able to extrude this around this hemisphere, or this axis here, to give you the results for the entire structure. So this is particularly useful for circular footings, single piles, and vertical wells. And then 2-dimension seepage analysis. Once again, there are certain assumptions that you have to make with seepage analysis in GTS. One, that geometry and boundary conditions are independent of the z direction. So once again, that just assumes that in the z direction the structure is uniform, so that you can extrude in the negative or the positive z direction and the results won't change, or that in the z direction the difference is negligible. Also, flow in the z direction is considered to be 0. So all flow has to be either in the x and y direction. Otherwise, you need to do a 3D analysis. And then application examples, long straight dams with toe drains, slopes and retaining structures, dewatering of long excavations, and then also embankments and earth dams as well. Okay, 3-dimension analysis. Once again, this requires the greatest amount of time investment. This requires the most amount of skill to do successfully, but it can be used for all types of projects. And it's not limited to projects that are symmetric and flow can go into the z direction. Once again, this is a higher level of analysis which will go on in some more advanced classes. But just to give you an idea of the sort of the power, the capabilities that lie within 3D analysis, I've included this here. And these are just a couple of examples. Pad footings, tunnel intersections definitely require 3D analysis, and also inclined piles or groups of piles would require analysis in 3D. Okay, now we just need to select the element types. So in midas GTS, you have 3 main element types available to you. So you have solid elements, which represent ground materials. Then you have structural elements, which are obviously non-ground materials. These are typically sort of maybe foundations, pile foundations, any type of tiebacks or retaining structures. These are modeled in a different section of GTS, which I'll explain later. And then last but not least, interface elements, which are specifically used to analyze soil structure interaction. So just keep in mind these 3 element types, and these are the 3 element types that you'll be using in any type of analysis. Oh, and just a quick note, so obviously in geotechnical engineering, depending on the project, you might need just 1 or all 3 of them, but with any type of geotechnical project, you'll always need solid elements or soil elements. Okay. And then order of continuum elements, so these are just different ways maybe that you can create your meshing. Linear elements as well as quadratic elements. These obviously are more detailed. They require greater sort of input, but they will give you sort of more accurate results. So depending on, like, these are typically used for maybe particular parts of the project that deserve a lot of sort of attention or that are of specific interest, you would use quadratic elements. But linear elements, they're simple to make, and they're typically used for sort of the broader spectrum of the project. Okay. And then structural elements, I won't go too in-depth here. Once again, once this project or this tutorial or the session is done, I'll send you all a copy of the this PowerPoint so that you can refer to it in the future. But here's just the different sort of structural elements that are available to you, as well as the element types that are used to model them. So you can refer to this chart later on as you're creating your own projects. Okay, then interface elements, which are once again are specifically used to model soil structure interaction. This is sort of a higher level of analysis. Maybe if you want to understand the effects of the soil on the ultimate skin friction of a pile, or maybe a foundation, you would use interface elements to simulate the friction and maybe certain failures that you want to look out for. So I won't go too in depth into this one today, but later on, once again, in more advanced classes, we'll go more in depth into sort of interface elements. The subject typically takes an entire course in and of itself because it can be very complex depending on the project. But once again, we'll go over that, and if you have any questions about it, as maybe you're remodeling one of your own projects, I'll be happy to help you out with it. Okay, and then mesh refinement or discretization. So the finer the mesh, the more detailed the analysis is. So as you can see, here's like a sample tunnel project. Now, the area around the tunnel would be of most interest because that's where most of the sort of stresses or strains are applied. That's where you want to check for failure. So the meshing around the tunnel is much finer as you go closer to the tunnel. And this is something that the program will typically do automatically. It'll sense where the meshing needs to be more fine. But this is also something that you can define on your own. And I'll show that to you in the tutorial that we have coming up. Okay. And then another thing that you always want to do is just to check the quality of your meshing. So sometimes when you're putting the meshing in manually, sometimes you'll have certain faces that aren't free. Maybe you'll have meshing that isn't as fine as it should be. For example, here in this tunnel intersection, the meshing should be very fine by this intersection here. So it's important to check that the quality of your meshing is up to par. Otherwise, your analysis won't be as accurate as you would like. So these are just a few things that you need to sort of be aware of: the skewed angles, warping, twists. But once again, because midas GTS has been developed to be more user-friendly, typically you can avoid all of these problems just by using the automatic meshing features, which I'll show you. And then defining the boundaries. Okay, so something that's really important to take into mind is that when you create your boundary conditions, you want to make sure to include enough area to include anything that would be of interest, but you don't want to make it so big where the analysis would become longer. So this is just another way to make sure that your analysis doesn't take too long, is to make sure you create your boundaries according to the rules of the slides, which I'll show you. So for example, shallow foundation, say here's your foundation. The length or the boundaries of your project in the X and the Y direction should be roughly according to these ratios here. And I won't go into too much detail about them, but once again, I'll send all of you just a copy of this this PowerPoint so that you can refer to these graphs or these or these guides when you're creating your own boundary conditions. So here's a good one for unsupported excavations. So the good rule of thumb is if you keep your boundary conditions within these ratios, it'll be a sort of good middle ground. So it won't be so big that your analysis will be too long or much longer than it should be, but it won't be too small where you'll miss out on certain maybe things that you want to keep in track of closer to your excavation or to the point of interest. So once again, gravity walls, diaphragms, embankments. So these are just good sort of guides to refer to when you're creating your boundary conditions. And then we also have boundary conditions for tunnels here. Okay, so once again, I'll send this to all of you so that you'll be able to have these references available to you when you're creating your boundary conditions for your own projects. Okay, perfect. So now that that part's done, what I'll do is I'll do some modeling. So for today's session, I have 3 particular tutorials that I want to run through with all of you. One will just be about basic 3D modeling as well as how to use a boolean cut, which I'll show you. Then we'll go over consolidation analysis, and then we'll go over seepage analysis. And lightly I'll touch upon drained versus undrained analysis, how to sort of toggle that option on and off with midas GTS. And then in our upcoming sessions next week, we'll go over pile and raft foundations as well as slope stability. Okay, so just give me a second and I'll open up the program and we'll get started on these tutorials. Okay, so just let me, I need a second to load up the files. This won't take very long. Okay, so I'll just open up a new file. Oh, and I see a couple of questions here in the chat box, so I'll just review those real quick before continuing. So sorry if I missed your questions. Okay. Oh, and so sorry, I forgot to mention. So this session will be recorded. So for those of you who maybe have colleagues that missed out on it, you can, I'll share the recording with you guys after it's done, and that way, you can share it with your colleagues who missed it, or if you want to review over it, you'll be free to do that. Okay. Okay. Okay, so I just need 1 second just to change the settings on my other screen here. Sorry, this is my normal computer. I'm having a little trouble with the GUI. Okay. Okay, so just a second, and I'll get the right file open. Sorry, I just need to find my folder. Okay, sorry guys, I'm just having a little trouble working this computer. I'll be back in just a second. Okay, guys, sorry again for the hold up. So I see a question here. So somebody wants to know why the z direction comes out, coming toward us in the start. So as okay, so sorry about that. So somebody asked why the z direction comes out to us at the beginning. So this is our work plane. So x and y would be sort of shown in these directions. So as you can see, you can change the orientation of the axis just using toggling these options here. But now let's just stick with 3D. So if you want to go to your isometric view, go here, and then you can have a very clear view of what's going on as far as your coordinate system. So let's get started with modeling just a basic 3D block. But first, let's take a look at our units. As you can see, your units are tons and meters. If you want to change your units, just go to Tools, Unit System, and you can change your preferences here. And then for time-based analysis, you can change these accordingly. Okay. So first, let's create our block. So the first thing that we want to do is to create our geometry. So just go to this geometry icon here, this tab. As you can see, you have many different options with which to create your geometry. So first, let's create just a very basic, let me turn on the symmetric view here. Let's create just a very basic, primitive a box. Okay, perfect. So I'll just use some preset values. 124, 100, and 100. Okay. And it seems that I'm not quite in the screen here. There we go. So, isometric, there's our box. Sorry about that, I accidentally hit the scroll button. So now that I have my block here, what I want to do is I want to create just a very detailed contour line through the middle. But before we do that, we still have a few more steps. So once again, I know I went through this a little fast, so I'll try to slow down. The walkthrough was geometry, primitive feature, and then just choose the box option. And once again, here are the different sort of options that are available to you if you want to create cones, cylinders, spheres, etc. Okay. So now we want to make this box transparent. So in order to do that, we would just have to go onto the work menu here. As you can see, whenever you create something, it's recorded here in the work menu. So let's go to geometry. And as you can see, I have my box. If I open this. So everything here is conveniently stored in the work tree menu so that you can record everything that you create. And if you right click on this option, go to transparency, or actually display mode, let's change this to a wireframe. So now the edges of your box are highlighted in blue, but you can see through it. So now that we're going to create a soil layer through it, we'll be able to see it very clearly. So once again, just the follow through, display mode, wireframe, and then you can have different sort of other options that are available to you as well. Okay. So now our next step is to create our grid face. So in order to do that, we need to go to geometry, then surface, create, and then grid face. So this is a very unique, oh, sorry about that, guys. I keep moving the screen out. So let me zoom in here. Okay. And once again, in order to change like the views on your screen, just refer to these icons here. So it's very easy to just change your viewing mode just through using these tabs. so now we want to create our grid face. So just go to Geometry, go to Surface, Create, and then Grid Face. So this is a very unique option that's available to you in Midas GTS, where you can actually take, for example, certain terrain values that you have inputted from other sources, and you can input them directly into the program. So first, let's enter a few parameters. So this is just the number of divisions in the X and Y direction. Okay. And now we just need to import our file. So in order to do that, we just need to click on elevation. As you can see, these are all 0 for now, but we'll import a file to change those. Go to load, and what you can do is you can look through your program to find the right file. So just give me a moment and I'll find the right text file to import. Okay, here we go. And as you can see, all the values are imported within a moment's notice. Click OK, and then apply. And as you can see, you have a very detailed sort of contour surface just imported directly into your grid. Okay, so now that we have our surface imported, what we want to do is we want to separate, or we want to divide our box here by the surface itself. So we want a section down here and a section up here divided by the curve or the contour here. So in order to do that, we just go to Geometry, this function once again, or this tab. We go to Solid and then Divide. Okay. And once you do that, this special menu comes up. So the first thing that we want to do is we want to select the solid to divide. So what we want to divide here is this box. So we'd select this, and we just select the entire box. So now it's outlined in red, so you know it's selected. And now we just need to select the tool. So the tool, or the dividing sort of criteria, would be the surface. So just select Tool Surface, and then press up on your directional arrow or your keypad so that you can select the contour itself. And now it's selected. So now make sure just to set up a few other options to check these off. Delete original shape. Excuse me. Make sure to leave these on. Delete original shape and to delete tool shape. So delete original shape, that just means that in addition to the two separate sections, you won't have the whole section itself. So that's just a way to say, for example, you don't want to keep the whole section. Or that makes it easier for selection. So if you select this option, once again you'll have the bottom section and the top section only. You won't have the whole shape. So that just gets rid of the old shape and creates two new ones. Okay. So now just click Apply. And as you can see, if you look closely, we have a top layer, or we have a bottom layer, and then we have a top layer. So that's how you can sort of use these tools to easily cut maybe surfaces or areas that are of interest to you. So it takes a little practice, but once you get the hang of it, you'll be able to create complex geometry within a matter of moments. And this is just one of the main tools that I use typically when I'm creating more complex geometry. So once again, just as a review, in order to do that, just go to Geometry, go to Solid, and then Divide, and then this option comes up. And then just to show you the other options that are available to you, if you go here, you can also trim materials. So say I wanted to cut this top section off, I would use the trim option. Embed, if I wanted to insert one section into another, I could use that. But once again, I can get more into the detail about those options later on. Okay. Okay, so now that we have this set up, let's create a cylinder, or let's input a cylinder into the drawing. So once again, we're going to stick with the Geometry tab, and then we're going to go to Primitive Feature. Once again, this is just the option or the section for all of your basic shapes, and this is just a shortcut that you can use to create them. So let's create a cylinder. So once again, once that option comes up, you'll see the cylindrical icon as well as this table. So I believe I have some coordinates ready, 62, 50, and 50. So that'll be sort of where the center of your cylinder will be located. So as you can see, I already have it sort of pre-planned. The radius, let's make it 2 meters. And then the height, let's make it 60 meters. And the angle, let's leave it at 360. Okay. So now that I have this ready, make sure this is checked on. And let's name this pile, just to be more specific. Click Apply. And as you can see, we now have a cylinder just inserted directly in the middle of our block here. So let's close this. And let's just give you a couple of better views. So once again, if you want to change the view with midas GTS, you would just refer to these icons. So here's your side views. You have your 3 layers as well as a cylinder. Then you have your top view, obviously, and your bottom view. Okay. So it's very simple, once again, just to create complex geometry, to insert your piles or foundations with midas GTS. It just takes a little practice, but once you get the hang of it, you'll be able to create very complex geometry, or you'll be able to create your project details within a matter of moments, just using the geometry icons here. So right now I'm just obviously just scratching the surface of how to use the geometry modeling, but I hope you're getting a sort of an awareness of how to model with midas GTS. Okay. So now that I have my cylinder inserted there, something that would be, or my pile inserted there, something that would be of interest to me would be to sort of separate, or to be able to select my pile based on different sections. So let's go to the side view. So say, for example, I wanted to maybe cut my pile according to these sections here. So say maybe I wanted to separate this part as well as this part, just to sort of maybe to get a more detailed analysis later on in post-processing. So in order to do that, you would just go to, actually one more thing I sort of forgot that I'll go over first before I go into cutting. Let's go over how to mesh. That's very important, discretization. So in order to do that, just go to Mesh, this top tab here, and then go to Auto Mesh, and then Solid, because once again, Face would be for 2D or planar elements, and Solid is for 3D elements. So since we're modeling in 3D, we'd need to use this icon, not the face icon. That's very important to remember. And then also, before I continue, another option that's available to you is if you would like to extrude a project or extrude maybe some 2D meshing, you can use this option as well. So as you can see, all of these meshing options are available to you. But right now we'll stick with the solid option because this relates specifically to this project. So let's go to solid. And then this icon or this menu will come up, and you just have to enter in certain criteria. So first, we need to select the solids that we want to have meshed. So select this, select the top and the bottom part, as well as the cylinder itself. So all of this will be meshed. Now we need to select the method size. So we want to divide it. And then we want a division of 10. Okay. And 10 is a sort of a standard option to use for a project this size. And then attribute, you can leave that blank. Okay. And then let's check out the advanced options here. So as you can see, if you want to be sort of more detailed about your meshing you can select the edges, the points, but once again we just selected the our solids, so we don't need to worry about any of that. So all of this looks good. Okay, close. All right, so let's apply. Oops, I have to define the property first. Sorry about that. So first, let's define. Since I don't have any material data inputted, I can just assign an arbitrary value. So just put attribute 1, and then the program will it won't assign any material properties to it, but it'll be able to run the meshing. Okay. And now the meshing has been done, as you can see. So sorry, I'm seeing a lot of questions here. Sorry I haven't been checking up on them as much as I should. So I'll just take a minute here. Okay. So you mentioned 3 layers. I see only 2. Oh, sorry about that. Yeah, I meant 2 layers, not 3. So you have the bottom layer and the top layer. So thank you for correcting me on that one, Amr. Okay. So once again, if you have any questions, feel free to type into the chat box, and I'll try to do a better job of addressing them in the future. So, as I said, Amr pointed out that I said 3 layers at the beginning, where in fact there are only 2. So you have the bottom layer and the top layer. Okay. So that's how you do your meshing for your 3D model. And before I continue, I'll just show you how to sort of view it in the wireframe. Or actually, just in the interest of time, I'll just move forward to sort of how to use the boolean cut, because I know that was something that was of particular interest to Amr when he emailed me. So I'll just fast forward here. So first, in order to see the boolean cut, I'll just have to delete the meshing for now. But once again, just as a quick review, to create your meshing, just go to Mesh, Auto Mesh, and then Solid. So there are different ways that you create your meshing, but this is typically the fastest way, Auto Mesh. It's the most convenient and user-friendly. Just go to Solid for 3D elements, and then just fill in, select your objects, and then fill in the criteria, hit Apply, and then your solids will be meshed automatically for you. Okay. So now once again, everything is recorded here into the work menu. So if I go here under Mesh, as you can see, I have 4 mesh sets. You have the default mesh, which is just included beforehand, and then I have the mesh for each soil layer, as well as the mesh for the cylinder. So let's just delete this meshing for now. And then I'll turn on the solid itself. So once again, you can use these icons as well to toggle things on and off. So say, for example, for larger scale projects, you'll have a long list of solids. In order to make viewing more easy, each sort of element or structure that you create will have these checkboxes next to them. And if you want to turn them off and on for easy viewing, you would just refer to this menu here. Okay. So now that I have my cylinder created, now I want to use my boolean cut. So in order to do that, I would just have to go to geometry once again. So once again, this particular tutorial is mainly using the geometry tab to create your project geometry, to make cuts, to make your meshing, etc. So go to geometry, and then go to boolean operations, so it has its own command here. And then let's go to cut. So select boolean master. So what boolean master means is essentially maybe the structure or the plane of interest that would be doing the cutting. So for example, I want to cut the cylinder according to the boundaries of the soil layer. So this soil layer here would be the master, because that's sort of the point of reference for the cutting. The tool would be the element that's being cut. So select boolean master. We'll select this top layer here. Okay. So it's checked. So it recognizes that this top layer is the boolean master. As you can see, it's highlighted in purple. And now we need to select boolean tool. So just select this. Once this arrow is here, you can now select whatever you want to be the tool. And then we'll select the cylinder. There it is. Okay. So now that this is ready, and also turn off delete tool objects, and then click apply. Okay, perfect. So as you can see, the cylinder has been cut along the top and along the bottom, which is where the sort of the cylinder or the pile intersects with your soil layer. So that's how you would use the boolean cut. So let's do another boolean cut, but this time let's use the bottom soil layer as the master. So select this. As you can see, the bottom is now the master set. And then once again, okay, select the cylinder. So make sure to select the whole cylinder, not the part that you cut, otherwise it won't work. And then click apply. Okay, and as you can see, you now have this bottom piece, which has been cut by this bottom soil layer. So that's how you would use the boolean cut for this particular application. And once again, the boolean cut can be used for not only pile foundations, but other, certain structures or elements that you would want cut according to your maybe a certain ground material or soil layer. So that's how you would use a Boolean cut. Okay, so that's just a basic sort of demo of how to model 3D objects with Midas GTS. And once again, your main point of reference would be the Geometry tab. This is how you create all of your geometry and objects. Okay, so I'm reading the question tab now. So Amr says, do you have to use the Boolean cut or can you use embed? Okay, so that's a very good question. So let me just refer to the left over here. So just give me a second. I just want to sort of set this up here. Okay. So, as I said, the cut is the better option, but if we embed the pile solid into the ground, the upper part above the ground will be deleted. Okay, so thanks for that question, Amr. And once again, if you have any more questions, if anybody else has any questions, feel free to type into the chat box, and I'll keep an eye out for anything that comes up. So now what I'll do is I'll just set up my next project, and let me just see if I can find it. And this will just take one or 2 seconds. Okay, so I just need another second here to find the right file. So I realize I'm muted, but once I'm ready to start, I'll let you guys know. So sorry, I just saw a question from Amr that I want to answer. So as you can see, the mesh is continuous. As you can see, these points here along the top connect with your cylinder. And just let me see if I can open up the free faces for you. Okay, so now if you want to check how the mesh is running throughout the inside of the model, you'd need to change it to the wire mesh. So in order to do that, you'd go to Mesh, or actually, first off, you have to go to the worksheet menu, excuse me, and then you'd have to hide all. And now you'd go to Mesh, check Mesh, and then you check for any free faces. So as you can see, the mesh is continuous and there are no free faces going throughout the sort of the center of the model. So through using this option here, you can see how your mesh is going out throughout the, the inside, I guess, of the box or the inside of your model. So let me just go through that method once again. So first off, you'd have to hide your mesh in order to, to see it transparently in the next step. You'd go to Mesh, you'd go to Check Mesh, and then you have all these different options with which to view your mesh. So go to Free Faces, because we want to check just to make sure our mesh is uniform throughout, and click Apply. And once again, you can see the wireframe of your meshing, and then you can sort of see the inside of your mesh. So this is an important practice to do whenever you're doing 3D modeling, is you want to make sure that there aren't any free faces. So thank you, Amr, for bringing that up. And once again, if anyone else has any questions or would like to see something in particular, please just let me know, and I'll stop with what I'm currently working on, and I'll make sure to answer your question. Okay, so now let's go back to my other model here. And as you can see, this is a complete model. So what I'll do is I'll just backtrack a couple of my steps, and I'll just sort of show you how this was done. So here I have my mesh sets, and I'll just delete the ones that I've created already. Okay, so this is just a sample seepage/consolidation problem. So once again, we're using planar elements, so all of this will be in 2D. So the first thing that we need to do whenever we have like a 2D drawing is we need to go to Geometry, we need to go to Curve, and then we need to go to Intersect. So we want to make sure that all of these lines intersect. What this feature will do is it'll take your drawing and it'll make sure that all of your lines are intersected properly so that your meshing can be created. If you don't do this, otherwise, you won't be able to run the analysis. So this is the first thing you need to do whenever you have your 2D drawing, is to make sure that all of your points intersect. So let me just go through that one more time just to sort of stress the point. So go to Geometry, go to Curve, and then go to Intersect. Okay, and now we want to select the whole drawing. So there are certain ways we could do this. The best way, or the most convenient way, would just be press Control A on your keypad, and the whole drawing will be selected, and just click Apply, and the program will take a minute to just make sure that everything intersects with your drawing. Okay, perfect. So now that we have that done, we'd want to create our material properties. So in order to do that, just go to Model, and then go to Property, and then go to Material Property. Okay. Oh, sorry about that. I see another question from Amr. So I did the meshing before you do the boolean cut. How did it become continuous? Okay, so let me just bring up the other model, and I'll answer that question. So just a second. Oh yeah, sure, Amr. Sorry, let me unmute you. That way, I think I can sort of understand you better. Okay, Amr, I should be able to hear you.
Yeah, Daryl, just a quick question. When you created the box and cut into two layers and then created a cylinder,
Yeah.
right? Then you did the meshing before you do any boolean cut or embedment.
Uh-huh.
It's different from this mesh that you show now. It was more of a coarse mesh. The mesh that created in the beginning, it was not continuous, right? Because you didn't do any boolean cuts or any embedment. You just put the cylinder in the box and meshed. Now it was not continuous, right?
That's correct.
This one it looks continuous because this one you did the boolean cut and then you meshed after that.
Yes.
Okay, but that's a big issue for us here. I mean, we
Oh, is
we
it? I didn't know.
start from the beginning in this.
Okay.
So we either embed or do the boolean cut and then mesh.
That's correct. Yeah. So sorry, I skipped over that point. I didn't realize it was that sort of critical for you guys. But yeah, you're right. You'd follow that process in order to keep the meshing continuous.
Okay. And there is no one of them preferred, because when we try to embed something, it created double element, like two elements twice. I don't know why. Like when we embedded an element in a solid, it sort of created a third element out of nowhere.
Oh, a third element. Okay. So let me bring up just the option here for you. So let's go to boolean cut, and I'll sort of show you. Okay. So whenever you create your boolean cut, once again, you select your master as well as your tool. So for example, in this particular project, the master sort of section would be the top layer, and the tool would be the cylinder, because that's the sort of section being cut. Now, the reason a boolean cut would be more effective for what you're talking about is because it has this option here where you can delete the tool object, or you can delete. So for example, when you have like a cylinder such as this, you said when you ever embed something, like a third element is created, correct? So
Yes.
using this option, if you select delete tool object, what will happen is it'll keep that element from being created. So in other words, it's a lot easier to sort of make your cuts without having to worry about that. That's why I sort of mentioned in my chat that instead of embedding, a Boolean cut would be more effective because it sort of takes out that extra step, or it takes out,
Okay.
what you're talking about.
One more question there. When you do a boolean cut, you cut the cylinder in the soil and the soil in the cylinder, or you do just one of them?
What you do, well, it really depends on what you set as the master and the tool. So for example, if I were to set, in my previous example, I set this top layer as the master, and I selected the cylinder as the tool. So in this case, what would happen is the cylinder would be cut. But if I were to sort of switch that, if I were to make if I was to make the cylinder the master and something else the tool, then whatever is the tool, I guess the simpler way of putting it is whatever the tool is, that's what's sort of being cut. So it really depends on what you define.
But I mean, what you did is enough to make sure it's continuous, right? If you just cut the cylinder into the soil, this is enough to make sure that the mesh is continuous.
That's correct.
Thanks, man. I appreciate it.
Okay, no problem. Yeah, and if you say for example after the session you need me to clarify some more, feel free to just send me an email. I know you've been in contact with Puya a lot lately, but feel free to contact me as well. I'm not as fully experienced as Puya, but I can definitely answer sort of simpler questions such as this.
Okay.
Okay.
Thank you.
Oh, no problem. Thank you for your input, definitely. Okay. So let me just go back to my previous project here. And once again, if any of the any of the other engineers would like to chime in or has any questions, you're more than welcome to stop me. Once again, this project is this training session especially for you guys. So just let me know how I can help.
I'm sorry, guys. I'm asking too many questions. But
It's okay.
we've been in this for about a month now, and we already developed too many questions. I know most of you, that's the first time to get exposed to it. But hopefully, when we ask these questions, you don't have to go through the same hoops that we went through.
Yeah, and definitely, because I know it takes a lot more than just a couple of training sessions to really become adept with the software. At Midas, we definitely make sure to provide full support to our clients. So if any of you other guys has questions after the session is over, feel free to email me directly. I'll leave my email address with you guys. And I check my email box every day. I answer questions all the time from clients, especially clients that are first learning how to use the software. So once again, I'm always available to you, even after the session. Okay, so where was I? So geometry. Okay, yeah, that's right. So now that I have my geometry created, my next step would be to create my my ground material properties. So in order to do that, just go up to Model, and then just go up to Property here. And then as you can see, you can create your material properties using these options. So let's go to Material. And as you can see, I already have these sort of predefined already. So I have my fill, and let's take a look at the sort of material properties that are available to you, or excuse me, the parameters that are available to you. So if you go to Modify, as you can see, you have your modulus elasticity, your shear modulus, saturated weight, permeability coefficients, which are, of course, essential for consolidation analysis. And then you also have your constitutive models. So because this is like a seepage analysis, I'm going to use the more Coulomb constitutive model. But I'd also like to show you all the different constitutive models that are available to you. So once again, I touched upon this slightly during the PowerPoint, but Midas GTS has all of the constitutive models that you would need for any type of analysis. It's just a matter of selecting the right one. So as you can see, as you go through the different material properties, or the different constitutive models, different options are available to you, or different parameters need to be filled in. But you should all be familiar with Moore Coulomb. So that's just a sort of basic sort of overview of the parameters that you would need to bring sort of ready to input into the program itself. Okay, so this is a simpler project, so I only have two different sort of material properties I want to use. One is fill, and then the other one would be clay. And another way just to check up on your material properties is just to go over here. And as you can see, everything that you create is just recorded into the work window, so fill and clay. So if you want to take a look at those, you can see the material properties here as well, if you want to double check to make sure that everything is on point. Okay. So now that I have my ground material properties defined, the next thing I would need to do would be to create my meshing. So let me see if I can set this up here. All right, so in our previous example, we meshed a 3D model or a block. But because we're with this particular project, we have a 2D or planar elements, we'd have to use a different meshing option. So just go to MEP, excuse me, go to Mesh, then go to Auto Mesh. Oops, wait a second, let me change the settings here. I'm sorry, I just have to change a quick setting to make these available. Sorry about that. So now I'm in pre-processing, so I'll be able to check the mesh. So once again, just to explain sort of what happened there, the reason that the meshing didn't show up was because I was in post-processing. In other words, I already analyzed this project before. I was just sort of reviewing the steps that I needed to take before it was analyzed. So whenever this lock here is selected, that means I'm in post-processing mode, which means I'm checking the results. And I can't change any of the geometry. I can't change any of the meshing. But if for any reason, say you've run an analysis and you want to go back and change something, what you would need to do is you need to select this option here, pre-mode. As you can see, the symbol is like an unlock sort of symbol, which means that meshing, geometry, material properties, you now have access to those, you can change those. So once again, we need to create our meshing. And since,
There, quickly, in a minute, you draw this using what lines?
Oh, I imported it from, for example, like an AutoCAD file.
Okay, okay. And you have all these lines for future drains or something, or what?
Oh yeah, well I have a couple of drains that I want to input. So I have a drain over here, and I'll show you how it's how I plan to do the draining. And another reason I have all of these lines is because I wanted the meshing to be sort of like a grid. So when you create sort of a grid pattern like this, the meshing just automatically sort of goes to that. And I'll show you that in a minute how that meshing is created. So yeah, if you go to Auto Mesh, you go to Planar Area, and all you have to do is go to Select the Edges. So the first sort of section that I want to mesh would probably just be like this top part over here. So in order to do that, just go Select Edges, and once this arrow is facing right, that means you can select the edges of interest. So what I'll do is I'll just box them in. And then for element size, I'll be, I believe it's 5. And then, so once again, you have to check your attribute as well. So since it's a top layer, it isn't clay, it's actually a fill, so make sure to change that. And then also, make sure to check your advanced options. So these are the different meshers that are available to you. Let's go with the D1A mesher, quadrilateral. And then we'll turn this off. Okay. And then another thing that's really great about GTS is you can actually sort of view how fine your mesh is before you before you run it. So for example, if you go to this tab here, as you can see, the mesh it isn't particularly fine. So what I can do in order to change that, we go to mesh size and change it to something more fine. So let's try 0.5. There you go. That's much better. So now the meshing is much more fine. We can get something much more detailed. So let's hit apply, and let's see if this meshes here. Okay, perfect. So not exactly what I wanted. It probably could have stood to be a little more fine. So if I had made it 0.4 or 0.3, it would have been more fine. But just in the interest of time, I'll just move forward and I'll do the meshing for these sections over here. So what I'll do is go to Select Edge, and then I'll just select all of this, so this whole layer right here. Okay. And once again, it's really important to make sure your attribute matches, your layer. So once again, this would be the clay layer, so I need to change this. Select clay instead. Go to Advanced Options. Make sure this is the same, and then register each mesh set independently. Make sure this is checked off. Otherwise, there'll be a different mesh set for each of these blocks here. So since this is all just one layer that's all sort of uniform, we can just have all of these under one single mesh set. So make sure this is checked off. So click OK. And once again, before I do my meshing, I just want to sort of get a grasp of how fine it'll be. So if you go click on this little tab here in the bottom left corner, you can see how fine it's going to be. So that looks pretty reasonable. So let's click Apply. And once again, I have that grid meshing. And once again, that's made possible because I have sort of that grid pattern in place already. Okay, so now that I have my mesh created, the next thing I want to do is to create my self-weight or my loading. So in order to do that, just go to Model, go to Load, and then go to self-weight. And this is very simple. So just type self-weight into the load set name. And then, so we're in the negative y direction would be the direction of the loading. So just put -1 in the y direction, and then click Apply. And then the program will recognize, now once again, will take into account, just the self-weight of the structure. Okay. And now that I have the self-weight, I need to input my boundary conditions. So now in order to do that, just go to Model, go to Boundary, and then just go to ground supports. Okay, and we'll just name this boundary conditions. And then, so what this does, if you check this on, it'll automatically sort of consider every single mesh that you have. But just to sort of show you how to select your mesh sets manually in case you want maybe a certain portion of your project just to have the boundary condition. What you would do is you'd check this off, obviously, and then you'd now have access to different mesh sets that are available. So you have the top one and the bottom one. So all you have to do is select the ones that you want to have sort of the boundary conditions applied to, and then once you're ready, just click Apply. And once again, you have your pins and your rollers there. Okay. So now that I have my boundary conditions in place, my next step would be to input sort of the boundary conditions for, my drainage conditions. So let me just turn this on. And actually, I have a chart that I need to refer to that I need to pull up. So just give me 1 minute while I try to find it on this computer. And in the meantime, while I'm searching for it, if any of you have any questions, feel free to speak into your microphone or just to type into the chat box. Okay, guys, sorry about the hold up. So yeah, I got the reference that I needed. So now that we'll be able to continue. Excuse me. So now that we have our meshing created as well as our boundary conditions, we need to create sort of our nodal head or water conditions. So in order to do that, just go to Model, go to Boundary, and then just go to Nodal Head. Okay. Once you do that, this option window or this input window will come up. So first, let's change the name to water level. And then we need to put in the value of our nodal, or first, excuse me, we need to select our nodes. So the nodes that we'll select will just be this entire sort of perimeter here of our soil layer. So just select on this option, and then you can just box in all your nodes here. And as you can see, once the nodes are highlighted in red, that means they've been selected. And as you can see, I accidentally sort of selected some other nodes. So this would be a good opportunity to show you how to yeah, just sort of box those in more. There we go. Perfect. So once your nodes are selected, you need to enter the value of your nodal head. So for this project, let's create a nodal head of 10. Okay. And then once that's done, you just need to click Apply. And once these nodes are in blue, that means that condition has been applied. Okay. And now we want to add some drainage conditions. So in order to do so, you just need to go to Model, once again, Boundary Conditions, and then we need to go to Draining Conditions, which would be located right over here. Once again, you'd refer to this sort of input menu, or this input tab, to create your draining conditions. So first, let's rename this to Draining Conditions. Then we just need to select the nodes. So as I sort of pointed out to Amr earlier when he asked the question of why I had this grid here, was to make it easier to sort of recognize where my drainage conditions would be inputted. So I just need to select my nodes, so it would be this row over here. And I just need to be careful here just to input only these nodes from this row. Then it would be this row, sort of in the thicker line of black. And this row. Whoops. Let's go from the bottom here. There we go. And these will just be the areas that will be drained. So I understand that Amr, he had some questions about undrained versus drained analysis. So this will just be sort of a good introduction on how to create sort of drainage conditions for your projects.
Daryl, I have a stupid question.
There's no such thing as a stupid question, Amr. So yeah.
This selecting window, the selecting window that you're using, in my version here, it comes shaded dark gray, so I cannot see anything through it.
Uh-huh.
You know the selection window that you use?
Yeah.
When I try to grab and select anything, it's like shaded gray.
Okay. Oh, I think I understand what you mean. Okay, so there should be just an option to sort of change that, because I have that. Well, there's another sort of an alternate version of not an alternate version, but there's another sort of computer that I sometimes use. It has that option toggled on. So like another way, a better way, you know, to sort of choose your drainage conditions, you know, just to avoid having to use that shaded window box, would just be through this. You know, you can select the curves instead of having to, you know, use that box. So you go to drainage condition, you select one, or you select your curves, and then you could just easily just go one by one.
Mm-hmm.
So that would, you know, I'm not going to go through the whole thing, obviously, but that's just sort of another option that's available to you. So you'd go to, you know, boundary condition. Okay. So now that I have my draining conditions inputted, I just need to create my non-consolidation boundary conditions. So in order to do that, just go to non-consolidation condition. And then I have, hold on, let me, sorry about this. Let me turn on my, my meshing first. Okay, there we go. So now that I have this option available to me, just type in, make sure to change the boundary set name just for easier reference in the future. So non-consolidation. And then it's the node, and then we just need to select this top embankment here to designate this as sort of a place that doesn't, or a section that doesn't consolidate. So once again, you could just use this window here, and then there should be an option that makes it possible to make the box transparent as you wished. So I don't know off the top of my head how that's done, but once I figure out, I'll definitely get back to you with that, because you know I know that can be sort of difficult as well. So yeah, I'll get back to you with that answer. So you have your node selected, make sure, and then just click apply. Once again, once this is in blue, you'll know that the condition has been applied. So before I continue, I just want to sort of let you know how you can check on your boundaries here, or the boundaries that you've created. Sometimes when you create so many boundaries, you can sort of forget which ones need to be created, which ones you've already done. So just go to Analysis on the Worktree menu, and under Boundary here, you have your boundary conditions, your water level, your drainage conditions, non-consolidation, and you can turn them all on actually. So as you can see, you can sort of see which sort of set applies to which. So that's just a good way to check up on your work and to make sure that you have everything inputted, according to your needs. So that's, oh, yep.
Daryl, what do you mean when you put 10-meter head on everything, or on the perimeter? What do you mean by this boundary condition? What is 10-meter head on the perimeter?
Oh, okay. So that's just the water level, or so the nodal head will be sort of 10 meters of water just along this whole block of soil here. So in other words, it's 10 meters of head that's uniform across the entire sort of block here. That's just another way. I mean, I guess maybe the clearer way of putting it would be, that's your water level. It's 10 meters of head.
I mean, 10 meter measures from where?
Okay. So, your point of reference would be 0. So your reference would be 10 meters from, actually, let me just sort of try to make this more clear for you here. Okay, so it would be 10, and 0, and that, that's 1.4. Okay, so let me see if I can sort of make this more clear here. Let me just find the right option. Okay, so what I'll do is I'll open up another file, or another GTS model file, just to make it a little more clear, because I think through this file you'll sort of really be able to understand what I mean by 10 meters. And I have it here on the other screen, but I'll bring it over in just a second. Okay. So your reference point is 0, 10, 0. Okay, so just to try to clarify, so over here, here's our origin right here, right in the center. So this would be our global coordinate system, and here's 0, and here's like 10 meters. So once you input 10 as your nodal head, the program will recognize that this area here is fully saturated. Does that make sense?
Not really.
Oh, okay.
Should be for the whole soil net, not just the perimeters, right?
Yeah.
Or you choose only the perimeter points.
Okay. Yeah, so like this part here, this soil here is what's saturated, not necessarily the embankment. So that's why I chose the perimeter and not the entire model, or not the. That's why I didn't include the embankment.
But the soil in the box itself is also saturated, not just the perimeter points, right? It should be applied for the whole clay layer.
Okay, yeah. So yeah, as we said, we can agree upon that the soil itself is fully saturated. So I'm sorry, I don't think I understand your question. So you're saying that you don't understand how the program can recognize that sort of this inside part here is saturated as well?
Yeah, because you apply this boundary condition on the perimeter points only.
Oh, I see what you mean.
You didn't choose the whole soil mass and say put ahead of this amount. You
Mm-hmm.
just applied on the perimeter.
Okay. So the thing is, like, once you choose your sort of boundary conditions, like, see you have your mesh set here. Once you select the entire sort of mesh or the entire perimeter, the program will recognize everything that's enclosed within the perimeter itself. So in other words, the program will recognize that the sort of anything inside the perimeter will be fully saturated as well, because you didn't just necessarily choose the perimeter, you chose the mesh set.
Okay. So you can apply this boundary condition to the mesh set.
That's correct, yeah. Yeah, just like, I mean, technically you're applying it, to the nodes, right? But, anything included within that perimeter, will be sort of taken into account as saturated as well, as long as you define it as such.
Okay.
Okay, yeah, so I'll try to sort of clarify on that later on. Once again, just in the interest of time, you can get back to me, or I can get back to you actually just to sort of clarify. I know it's not fully clear. It's sort of harder to sort of grasp. But I'll definitely get back to that question later on. Okay. So now we just need to, because I believe in your email you discussed wanting to discuss drain versus. Okay. So now I see that we're sort of running low on time. So I'll just finish up this this demonstration, and then what we can do is we can approach further topics later on in the next session, which will be Tuesday, which will be an even better opportunity, because during that session we'll focus purely on the modeling itself. So we'll have more time to focus on just the ins and outs of GTS. So now I'll just finish up by running the analysis, or first I have to create the construction stages. Okay. So, as I said before, another great sort of feature of finite element analysis software is the opportunity to do construction stage analysis. Oh, I'm sorry, I think I see a question here. Okay, so somebody typed in a question. Sorry, I just need to open the box here. Okay, so somebody asked if there would maybe be an easier way to enter the water table, or the water levels, by simply just entering the water table. So yeah, that's absolutely another way you could enter the water table. So as you can see, if you select this option here, okay, so you're right there. We can easily just define the water level, as you said, but because this is a seepage problem, we need to define the nodal head. So that's why simply defining the water level wouldn't sort of suffice for this particular project. But as you said, for other projects, for example, slope stability or basic foundation projects, creating the water level would simply just would be very simple or very easy to do. But because this is a seepage problem which takes sort of nodal head into account, we needed to enter that instead of just entering the water level. But yeah, thank you for bringing that to our attention, definitely. Okay. So we're just about to wrap up here, but let me just first create the construction stages. So in order to do that, first we just need to define the construction stages. So actually, let me just show you how to get there. So in order to do that, you just go to Analysis. You'd go to Model, and then you'd go to Construction Stage, or you'd go to Define Construction Stage over here and over here. Okay. So the first thing we need to do is obviously just define our first construction stage. So we click on New. Oops. Or actually, we just go on this one here. So, as you can see, I've already actually created all of my construction stages. Perfect. So what we can do, let's just do here. Just delete this one. Okay. So I already have my construction stages created, but let me just sort of show you basically what I did in order to create them. So as you can see, you have your sets of data here. You have your different mesh sets as well as your different boundary conditions, as well as your different loadings. And what you need to do is you need to just drag and drop the mesh sets and the boundaries that are of interest to you from this area to this. So let's go to fill. Actually, let's go to our first stage, stage number 1. So for this first stage, what we'd need is the clay layer. So the clay layer, I believe, is this bottom one here. And then we'd also need our boundary conditions. So we need our, obviously just our regular boundary conditions, our ground support, which is our ground support, and then we'd need the draining conditions as well as a water level. So just drag and drop, and then the self-weight. Okay. And then, once all of our conditions are created, we would just save it. So that would be, our first construction stage. So we'd save, and then we'd have another construction stage. So say, for example, fill 1. So for this construction stage, the main thing that we need to take into account is just non-consolidation. So we just drag and drop it over, and then we click Save. And then also another important thing is the user-defined step. So let's go to that really quick. Okay, let's make sure to activate that. And as you can see, I already have my steps available to me, or my steps created, excuse me. So for this particular time step, I had 40 days with 20 step numbers. So I just typed in 40, excuse me, and then I typed in 20, and then I clicked OK, and then the program automatically divided for me. I generate my steps, and as you can see, the program generated my steps for me. Okay. So this is a good thing to do if you want to, say for example, you have a consolidation that's taking place over an extended period of time. Say you could have 40 days and 20 different iterations or 20 different periods of time that you'd want to analyze, so that you can see how your consolidation is happening over that 40-day period in sort of those sort of 20 increments. So that's how you create your load step. Perfect. So now that I have that created, all I need to do is create my analysis case. So just go here. As you can see, it's already created, but say for example I didn't have my analysis case, I would just go to Add. I would name it seepage analysis, or actually a consolidation. And then the analysis type would be construction stage. Now this is construction stage because we already defined all of our sets and our activated and deactivated elements in a previous step. If I were to run a seepage analysis, for example, I would have to do all of those previous steps in this case instead. But we'll get more into sort of a seepage analysis case, a pure seepage analysis case in our next session. So once again, it would be a construction stage analysis. All of this is grayed out because we already completed this step. And we click OK or Apply, and then our stage is created. Okay. So just in the interest of time, what I'll do is I'll just open up a previously sort of analyzed model file, just so that we can sort of speed up the process here. We're sort of running low on time. So I believe this one. Oh, perfect. Okay. So once again, in this particular file, the analysis has already been run. The analysis might take a minute or two depending on how detailed it is, but just to sort of save time, I just opened up this completed one. And once you're in post-processing, or you're analyzing your results, you just click on this tab here, Post, and as you can see, all of your results or all of your steps, are clearly sort of listed along with your different stages. And let's open up this particular time step, step number 7. And as you can see, all of your results are just very clearly listed there for you, so you can check your displacements, your strains, your stresses. So let's take a look at our strains here. So obviously these are the same. Actually, it might be better to go to the last load step just so we can get the most sort of the strongest or the most clear results. And if you go to this tab here, you can analyze or you can view how your sort of results change over the different load steps. So as you can see here, the pore pressure, how the pore pressure is changing over the course of your consolidation, which once again is one of the benefits of finite element software, is just the detail or the level of detail of your analysis or your calculations. So let's take a look at displacement. And let's just toggle the settings here. See, you can get your deformed shape, or this is actually just a very sort of exaggerated view of your deformed shape, but it gives you a better idea of what the consolidation, or how the consolidation would happen, or how the displacements would happen. Okay. And what I'm doing right now is I'm just going to look for sort of another file to show you, just to sort of give you another sort of idea of the post-processing options that are available to you with GTS. Okay, so what I've opened up here is just one of our more advanced tutorials on consolidation. So the previous example was sort of very basic. It just included sort of the basic things about consolidation. But this particular tutorial goes into much greater detail about the post-processing options that are available to you as it pertains to consolidation. So as you can see, you can create your graphs for time versus settlement, excess pore water pressure versus time. So all these time-based analyses can be sort of viewed with midas GTS. So what I'll make sure to do actually is I'll make sure to just send you a copy of this tutorial because I'm sure that the tutorial that I went over was maybe a little too simple for you guys. So this one will go into more detail. This will help you to sort of get a better understanding of the post-processing options that are available to you with GTS. And it goes very step by step in how to not only create the model but how to interpret your results accordingly. So that about does it for this session. Once again, I'll send you guys a recording along with the tutorials that I went over so that you can practice them on your own time. I do apologize for the technical difficulties that we had today. It won't happen again. I'll make sure to get the audio correct next time. But thank you for your patience. Thank you for your questions, especially Amr. And once again, I'll look into just trying to sort of explain those particular points a little better. I'll send you a follow-up email once I get maybe something a little more concise arranged. But before we wrap up, do you guys have any sort of last-minute questions for me?
I'm good, thank you, Daryl.
Okay, not a problem. So once again,
I have a question. I don't have any more. So see if anyone has a question.
Okay, perfect. So yeah, I'll make sure to just I'll send you a copy of the the session materials that we went over today, the tutorials, the recording, as well as the presentation, so you guys can review it on your own time. And what I'd encourage you guys to do is to try maybe one or two of the tutorials that I send, so that way you can sort of see how to do it, for yourselves. And if you have any questions at all about what you're going over, or if you get stuck, feel free to just give me a call or to send me an email, and I'll get back to you, usually within the hour. But thanks again for your time, for your attention, and I look forward to meeting with you all again next week. And enjoy your weekend, okay? Take care, guys.
Thanks.
Thanks.